Am I? Hope I am.
Мы на YouTube.
Pardon me?
Ну, идет трансляция.
Great. It worked. Fine. So last time we formulated the main theorem about the construction of reducible representations of X algebra and the characters of these representations and also the projective models over the X algebra and their characters and the Cartan matrix that expresses projectives in terms of irreducibles. So we still have to prove this latter theorem, and we will do so. But I wanted to recall this key point that the X algebra had some grading that was a little bit unnatural, and in this unnatural grading, the classification of reducibles and realization of reducibles was very clear. But I just wanted to remark that there is a particular case when the grading on the X algebra is the natural one. Namely, when this resolution morphism when this is semi-small. So we discussed this a little bit, and we had a notion of small morphism. And what does it mean? That N is the union of strata. Yes. And these strata are usually the orbits of some group that has finitely many orbits on N. And this morphism pi is stratified. With respect to this stratification. And for any S, the codimension of the corresponding stratum in N is at least twice the dimension of the fiber over any point here. Okay. And
Misha, sorry, what does mean morphism is stratified? I mean, like you just stratified the source, the target, and then you just take pre-images. What's stratified morphism?
That the restriction, the morphism to any stratum is just a fibration.
Okay.
is vibration, locally trivial. Okay, and the main example that is relevant in our case it is when this element A in the extended group is just one. And so in this case, N is just the nilpotent cone, and M is just the cotangent bundle of the flag variety. That is the Springer resolution of the nilpotent cone. And then, according to Grothendieck-Springer, the Springer resolution pi is semi-small, and in fact, so-called strictly semi-small. That means that the codimension of any nilpotent orbit is exactly twice dimension of the Springer fiber. Okay, and just by the base change and the usual topological cohomological dimension, this implies that the direct image of the constant perverse sheaf on the resolution is perverse. So it is the direct sum of certain IC sheaves with certain multiplicities. But in this case, the multiplicities are just spaces in degree zero, vector space, not graded. No grading. And in particular, this direct image is a semi-simple perverse sheaf on M. Okay, and in this case, the Hecke algebra, the Borel-Moore homology of the Steinberg variety of triples is the Hecke algebra extomorphism from this direct image to itself, and this grading is natural. So the zero part is the direct sum of endomorphisms of L phi, and X bigger than zero in positive degree is the radical. Okay. So again, in this basic example, everything is very natural. In general, you need to somehow rearrange the grading to obtain the similar result. Okay, so last time we ended up formulating the theorem about Cartan matrix. So let me recall it and prove it. The main theorem, I mean the last theorem from the last time was as follows. So under the two parity vanishing conditions, the Cartan matrix is computable in terms of Cardinalistic matrix and some diagonal matrix. Okay, so here the conditions are as follows. First, for any point in the base, the odd Borel-Moore homology of the fiber vanishes. Second, or maybe this was second, and the first is that the odd Borel-Moore homology of the Steinberg variety of triples also vanishes. Okay, and maybe just to recall that the Cardinalistic matrix by psi was by definition the sum of all stocks of Cardan. Sorry, stocks of irreducible perverse sheaves at the point in the orbit. Okay, so this is just the stock in particular degree, but the equivariant fundamental group acts there, and we take the multiplicity of irreducible representation number number 5. Okay, so here phi is the parameter of irreducible local systems, so it is the orbit and the local system phi on this orbit. Okay. So maybe chi phi is an irreducible representation of the equivariant fundamental group, and is the same as just irreducible local system L phi on all phi. Okay, so this is the Cardinalistic matrix, and there was this diagonal matrix D, and D, sorry, D phi psi is the Euler characteristic. So you see, in Cardinalistic matrix, there was just the sum, not alternating sum, but the sum, and here it is the alternating sum. And here we take L psi dual tensor L phi. Okay, and this is almost diagonal. Meaning that both L phi and L psi live on the same orbit. Oh, okay. So this was some recollection about the last theorem of the left time, and now we are going to prove it. And to prove it, we will formulate two basic lemmas.
Misha, sorry,
Yeah.
what is I phi?
What is I phi? And where do you see I phi?
Like-
I see. I phi is yeah, here. It's an embedding, closed embedding of a point x into, well, into everywhere, into the whole. Sorry, into the whole n, but this point is a point in the orbit of phi. Okay, so you take a stock at any point in the orbit. Certainly doesn't depend on the point of the orbit, on the choice of a point in the orbit. Okay, so we'll need two lemmas, and the first lemma is that if the odd cohomology of any Springer fibers vanish, then for any summoned in the direct image of the constant sheaf, so we write it like this. Yes, so this irreducible IC phi is a direct summand of the direct image of the constant perverse sheaf. And X is a point of the closure of some orbit, then the cohomology in degree, I will say what it means, of the cos stock of this IC sheaf is 0 for odd k, and here d phi is the dimension of our orbit. Okay, so in this basic example on the previous page, where we had just nilpotent orbits, the nilpotent orbits were all symplectic varieties, so they had all even dimension. But in general, you may have odd dimensional strata. So well, you need this. Okay, this will be our first lemma, and the next lemma is another parity vanishing result. So under the assumptions of the theorem, for phi and psi such that I see phi and I see psi are direct summands in the direct image. We have the parity vanishing for X between these irreducible sheaves. So in degree d phi plus d psi plus k. So this is 0 for odd k. So these are two lemmas, and now let us deduce our theorem from these lemmas. So somehow the main slogan is so to say no cancellations, because of this parity vanishing. In Euler characteristic, we don't have alternating sums. We only have all pluses or maybe or minuses, but no cancellations. and because of this, you can keep track of all the individual summands from the total Euler characteristic. Logan, relative anything. Means no cancellations. In the Euler characteristic. Okay, so now the actual proof. So we take any sheaves F1 and F2, just not necessarily sheaves, just any complexes on the base, and we compute the Euler characteristic of their acts. And this is again the Euler characteristic of the cohomology with coefficients in internal or ext or hom. Okay, and well, as I said, there's just the Euler characteristic with coefficients in this internal hom. But the Euler characteristic can be split up over all the strata, over all the orbit. Okay, so this will be the Euler characteristic of this particular orbit with coefficients in the co-restriction of this internal hom. But since the internal hom involves the Schrieg tensor product, it commutes with the Schrieg restriction. Yeah, for example, if you take just the usual product, usual tensor product, then it commutes with taking usual stocks. Yeah, it's sort of, you can compute point-wise or stock-wise. And dually, the same applies for costocks and the Schrieg tensor product. Okay, so this last thing equals the sum over the orbits, Euler characteristics of the orbits with coefficients in restriction, co-restriction of one sheaf, and then you take Schrieg tensor product with co-restriction of the other one, and now we take F1 irreducible IC and F2 irreducible IC phi, and now we compute this Cartan matrix. Well, no, maybe I should go to the next page. Maybe let's go to the next page. So this is our Cartan matrix entry, and as we argued last time, it is just the sum over all k. The x dimension from IC sub c to IC e. So this was our one of our key computations last time. Yeah, when we realized the projective models as the direct sums of the X algebra itself. Yeah, we applied the projectors, and this was sort of tautological last time. Yeah, for the same price as the computation of irreducibles. Okay, and now let's rewrite this because we just on the previous page we learned how to compute the alternating sum of x, right? Here in the beginning of this computation, we can compute the alternating sum of x. And here, instead of alternating sum of x, we have just the sum of x without signs, right? But the parity vanishing will make sure that these two coincide. So let's compute. First of all, let's rewrite this as the sum over all k of x in dimension d phi plus d psi plus k. It is harmless because anyway we sum over all the integers, and now this is by the parity vanishing assumption. This is the sum over all k minus 1 to the power k dimension of x d phi plus d psi plus k of I see psi to I see phi. Okay, and this is negative 1 to the power d phi plus d psi. The sum over all orbits, Euler characteristic of the orbit with coefficients in the co-restriction of the dual IC psi, Schwick tensor product, co-restriction of IC phi. Okay, and we're almost done. So now in the K group, of one particular orbit, the class of the co-restriction of our Gareski-McPherson sheaf is the sum of its cohomology. Okay, but we know the cohomology parity vanishing, so we can rewrite it as this. Okay, and this is minus 1 to the power d phi. Okay, and finally, this is just we replace the alternating sum by the usual sum by the parity vanishing. of lemma 1. Okay, so now we are almost done. So we will only have to use lemma 2 somehow. So let me sum up what we have. We have that the restriction, co-restriction of our irreducible sheaf is -1 to the power d phi of the sum over all integers and all irreducible local systems on this orbit. Okay, let me write it below. So this will be the sum of the multiplicity in the co-restriction of our sheaf of this local system times this local system. Okay, and this is in the K group of equivariant sheaves on the orbit. Okay, so the sum runs over the irreducible local systems on the orbit O. Okay, so we computed this co-restriction for one IC sheaf. Now we need to do the same computation for another one, and then we need to tensor them and compute the other characteristic with coefficients in this tensor product, right? So that's where we will use lemma 2. Okay, so we'll go to the next page and compute similarly for the other local system, for the other IC sheaf, but it has to be dualized. Anyway, we get -1 to the power d psi, and the sum over K and L again. So we take cohomology of the co-restriction of IC psi now with coefficients in L. But since we dualized, now we take not L, but L dual. Okay. So we have the same multiplicities, but these multiplicities are of the dual local system out of this one. Okay. So what we get is that the strict tensor product of dual IC psi and IC phi is the product of those -1 to the power d phi, or maybe I want psi first. Sum over integers and local systems, cohomology in degree d psi plus k of the restriction IC psi multiplicity of L times -1 to the power d phi, the sum over k and some other local system, and here we have d phi plus k. Oh, sorry, maybe not k. Maybe let's take some other running index like L. Okay. Again, restriction correlation to this orbit. I see phi multiplicity of L prime, and now we take the tensor product, the dual of L and L prime. Okay, and we are almost done, because by definition this is -1 to the power d psi d phi plus d psi, the sum over all pairs of local systems. Here we have the Cardinalistic matrix psi L entry times Cardinalistic matrix phi L prime entry, and here we have again L dual tensor Schrick with L prime. Okay, but for local systems, there is no difference between the Schrick tensor product and the usual tensor product. Maybe up to an even shift in cohomological degree. So in the K group there will be no difference whatsoever, and it remains to compute the Euler characteristic. And maybe multiply by this extra sign. Right. So what do we get? We get -1 d phi plus d psi, the Euler characteristic of the orbit with coefficient in the co-restriction of dual IC psi Schrick as a product with co-restriction of IC phi. This is equal to the sum over pairs of local systems of Cardinalistic matrix EL times Cardinalistic matrix. Oh, sorry, it was not. It was psi. Sorry. Prime times the Euler characteristic of this orbit with coefficients in L dual tensor L prime, and that's what we wanted. That's the product of two Cardinalistic matrices and this almost diagonal matrix D. So there we are. We deduced our last theorem of the last time from two parity vanishing lemmas. Okay, now we have to prove the lemmas. Maybe let me recall the statement of the lemmas first. So this was the first lemma. So under the condition of parity vanishing of all Springer fibers, we know that the costalks of the IC sheaves entering the composition of the direct image of the constant sheaf from the resolution only live in degrees of the same parity determined by the dimension of the corresponding orbit where we restrict. And morally, this is clear because when you compute the direct image of the constant sheaf from the resolution, then by the base change, its cos-stocks are the same as Borel-Moore homology of the stocks, right? Of the Springer fibers, and we know that the Borel-Moore homology of the Springer fibers vanish in odd degrees. So the same holds for the cos-stocks of the whole thing. Now, cos-stocks of the whole thing decompose into direct sum of irreducible sheaves, IC phi, with certain multiplicities. And so if you had any cos-stocks of those irreducible IC psi's, they would contribute into this direct sum. But we know the direct sum does not have any odd cohomology. Okay, so you only have to keep track of the exact degrees. But morally, this should be definitely true. So let's keep track of the exact degrees. Okay. So we said small m is the dimension of our resolution m, and let I be the embedding of our point x into the base. And then we know that the homology of the fiber by definition is the negative cohomology of the cos-stock. I mean, we should take the cohomology with coefficients in the dualizing sheaf, but this dualizing sheaf is just the constant sheaf shifted to the negative degree to m, and so its perverse sheaf shifted to the negative degree m. Okay, so this we can decompose. The direct sum of the multiplicity spaces. So these multiplicities are graded, as you remember. Maybe I will recall it momentarily. Okay. So here, once again, phi is the pair of orbit and irreducible local system on it, and we know that the direct image of the constant sheaf was direct sum over all phi. I see phi shifted by k, then there this multiplicity space left. LC, well, the graded k part. So LC altogether equals the direct sum of LC of k over all k. Okay, so now if x lies in this particular orbit of phi, then when we take the cos-stock of IC phi itself, then we know that this Gareth-Macpherson sheaf in the on the open part is just some local system shifted to the negative dimension. Okay, and so we get L phi to the negative d phi, the stock at x, and so maybe let me repeat once again. The IC sheaf over the open orbit is this local system that lives in the negative degree equal to dimension, in the degree negative d phi. But then you take not its stock, the stock would be in the negative degree, but you take its costock. But the costock will live in the positive degree d phi. Okay, so that's why I write here minus d phi, because I'm taking costock, right? So what do we get? We get that the cohomology degree d phi of the costock IC phi is the zeroth cohomology L phi over x, and is not zero. And so we see that the cohomology in degree negative j of this costock IC phi shifted by m plus k is not zero for the condition negative j plus m plus k equals d phi. Okay, so for k equals d phi minus m plus j, the summand L phi of k tensor h minus j of the costock of this orbit in degree negative m plus k gives a non-zero contribution to the jth Barrel-Moore homology of the Springer fiber if the multiplicity space is non-zero. Okay, but we know that the odd Barrel-Moore homology of the fibers vanish. I mean, this is our assumption, lemma 1. So this parity vanishing assumption implies that the multiplicity space in degree d phi minus m plus j is 0 for odd j. Okay. Now let x live in some arbitrary orbit. So far, you see, we considered the summed IC phi, and we took the point x in the corresponding open orbit O phi in the support of IC phi. Okay, but now let's take arbitrary point. So it will live here arbitrary atom in the closure of phi. Okay. Then similarly, we will get that L phi of k, this graded multiplicity, tensor h minus j plus m plus k of the restriction to x, or co-restriction of IC phi is 0 for j odd. And maybe let me let me call this conclusion. Trick. And if we assume that our IC phi enters this direct image with non-zero multiplicity, then from this first conclusion, the star conclusion, we get that for some integer p, the multiplicity space b phi minus m minus twice p does not vanish. Okay, and now take k equals d phi minus m minus 2p and substitute into the second conclusion. Here is our second conclusion for parity vanishing of the Kostok's with multiplicity alpha k. So we get that cohomology in degree d phi minus j minus 2p of the Kostok of IC phi is 0 for odd j. Okay, so all in all, we get the cohomology in degree d phi plus j of the Kostok IC phi is 0 for odd j. Okay, and this is what we wanted to prove for lemma 1. Okay, now let's recall and prove lemma 2. Lemma 2 was about a parity vanishing of x between irreducibles. Here it is in the upper part of this page. So we have two reducible sheaves entering the direct image of constant sheaf, and we wanted to prove that their x all lived in the same parity determined by the dimensions of orbits. Okay, now let's go and prove this. So we know that the x between IC phi and IC psi is the case cohomology with coefficients in their internal home. Now we know that the dual of IC phi is the Garesky-McPherson sheaf again of some orbit, but with the coefficients in the dual local system. Okay, and since the direct image of the constant perverse sheaf on the resolution is self-dual, we see that IC phi enters this direct image if and only if it's dual. Enters the direct image. So we have to check that the cohomology in degree d phi plus d psi plus k with coefficients in the Schwick product, Schwick-Panzer product of IC phi and IC psi vanishes unless k is even. Okay, so again, by the conclusion on the previous page, yes, the disparity vanishing. The multiplicity spaces vanish in some particular parity degrees. Okay, so by this there are integers p and q such that L phi multiplicity space in degree d phi minus m minus 2p. So m was the dimension of the resolution space is not zero, and the multiplicity space for L psi in degree d psi minus m minus 2q is also not zero, and from this their tensor product is not zero. Oopsie. Okay, but now the Borel-Moore homology of the space of triples of this fibered product is the ext, as we proved last time, in degree negative j plus 2m between the direct images. Okay, and sorry, just one moment. Okay, sorry. So you are right. This as a, the negative J cohomology of the product like that. Okay, and now you decompose into direct sum over all pairs of integers and pairs of irreducible sheaves. So L phi of K, the multiplicity space, tensor L psi of L, tensor this cohomology negative J plus K plus L plus 2M of IC E Schlick product with ICP. Okay, and by our parity vanishing assumption, the parity vanishing assumption for lemma 2 was that the Borel-Moore homology of the variety of triples was 0 for odd J. So the left-hand side is 0 for odd J. And hence all the summands in the right-hand side vanish for K equals d phi minus m minus 2p and L equals d psi minus m minus 2q. So we conclude that 0 is the cohomology in degree minus J plus K plus L plus 2M of IC the Schlick product with ICP. Okay, and this is H minus J plus E plus D C minus 2P minus 2Q of ICP Schlick product with ICP. If for odd J and hence we conclude what we wanted, that the cohomology of dphi plus dpsi plus A of IC Schlick ICP is 0 for odd K. That's what we wanted to prove. Okay, so lemma 2 is also proved, and well, congratulations. So finally, we proved that we computed the Cartan matrix under the parity vanishing assumptions that hold in our case. But we didn't actually check that they do hold in our case. That's some deep result of Lustig de Concini, Procesi, and others. Okay, so now one thing remains unproved, namely this somehow not vanishing result. I mean, we classify the reducibles and we realize the reducible representations of the specialized affine Hecke algebras in some multiplicity spaces. But we don't know actually if these multiplicity spaces exist or they vanish at all. And the important part of this theory is to guarantee that the multiplicity spaces do not vanish. So if the local system appears in the cohomology of Springer fibers, then the corresponding multiplicity space is not zero. And this will be the complete classification. So far, we only have, so to say, the upper bound. We know that the irreducibles are classified by those multiplicity spaces, but maybe some of them are zero. So maybe there are less irreducibles than the corresponding IC sheaves, the orbits and the local systems. So in principle, one has to prove this non-vanishing result. But since we only have some part of today and the next class, we will not have time to do this. I'm sorry. But instead, let me sketch another application of this technique for the proof of actual Cardinalistic conjecture for multiplicities in Fermat modules of irreducibles in category O over semi-simple Lie algebra. Okay, so now we are saying goodbye to the affine Hecke algebras and doing something else that I mentioned a few times. This Cardinalistic ideology to the Cardinalistic conjecture about multiplicities of irreducibles in Fermat. Okay, so here W and Y are elements in the while group, and usually the Fermat modules and irreducibles are numbered by not the elements in the while group, but by their highest weights. But the highest weights are as follows. So MW has the highest weight. W rho minus rho, and the same for Ly. Y rho minus rho. Okay, these are regular weights in the W orbit of sorry the rho itself. Sorry, of zero. With respect to the so-called dot action centered in negative rho. Okay, at least all those guys have the same central character. So they all have the same trivial central character. Okay. And in fact, all the Verma modules with trivial central character are of this sort, and all the reducibles with trivial central character are of this sort. Okay. So to this end, we will just, in a sense, repeat what we said before for affine Hecke algebra, but we will need just a slight technical extension. So we will need the notion of equivariant Borel-Moore homology. Or more generally, equivariant cohomology with coefficient in equivariant complexes, constructible complexes. And let me say a few standard words about this. So when you define equivariant cohomology for the action of some group G of some space X, on which this group acts, certainly, and with just constant coefficients, then by definition, due to Armand Borel, this is the usual cohomology of the classifying space of X. And what is this? Well, we have the classifying space for G. So there is some contractible space, e.g., with the action of G. So there is some then G torsor with the base BG. And so you see GX here and also GX on X. So BX, by definition, is the product of EG X under G. Okay, so the quotient of EG times X with respect to the diagonal action of G. Okay, so in particular, you see that BX also maps into BG, and hence this equivariant cohomology of X is a module over the cohomology of BG, and this is, but just by this definition, nothing but the equivariant cohomology of the point with complex coefficients. Okay, and then it is known that for G a torus, then this cohomology algebra is concentrated in even degrees, and so it is just strictly commutative, and it is equal to the functions on the corresponding Lie algebra. and for general G with the Cartan torus, and the corresponding Weil group, then the cohomology is again concentrated in even degrees, and they form just the W invariant part of this. Okay, and you might argue that this BG is some topological construction and not very suitable for our algebraic geometric setting, but in fact any G is an algebraic subgroup of GLN. Yeah. I mean, has some effective representation, and hence, well, there is a morphism BG into BGLN, and there's a fibration with fibers GLN over G. Okay, so if you want some algebraic construction, it suffices to do one for GLN, and for GLN, BGLN is the union of Grassmannians and M as M goes to infinity. Okay, and similarly, E GLN is the union of so-called Stiefel spaces. And M as M goes to infinity. Okay, so then we see that BG is again the union of Stiefel and M modulo G as M goes to infinity. So you see that actually everything has a pretty explicit algebraic geometric construction. And now, given an equivariant constructible, well, maybe I should say not maybe I should say not in this modality. Maybe I should say that, but by definition, an equivariant constructible complex on X with respect to G is a compatible collection of complexes or constructible complexes on those guys. On the finite dimensional approximations of BG. Okay, and the equivariant cohomology of X with coefficients in some constructible equivariant complex, by definition, is again the limit of the usual cohomology of these approximations with coefficients in corresponding complexes there. Okay, so that's how. Well, in fact, there are various approaches to this theory of equivariant derived category, but this is the classical approach of Bernstein rules. So the same Joseph Bernstein as the one with the Bernstein representation of affine Hecke algebra, and the same Weatherly Lunds as the host of a famous summer seminar. Okay, so now we will apply this machinery theory. So in our situation, at least for some long time, our G will be just a torus, torus T, acting on some space N, and then in the previous application, N would be like the nilpotent cone of some Lie algebra, and the next time application, this N will be certain Zastava space related to this algebra, and then F will be a semi-simple complex. That is, again, a direct sum of certain IC sheaves, like this, on N. And for IC sheaves, the equivariance condition is just, well, it's just a condition. It's not like extra structure as we had in the abstract theory before, but it's just a condition that the every IC sheaf is a minimal extension of some local system. So this local system must be equivariant with respect to action of T, nothing else. Only when you want to define, say, equivariant cohomology, then you will need some extra effort. But the notion of equivariance is very straightforward here. Okay, so I should say that equivariant. T equivariant complex, and our basic, so the main object, the key object of our study, will be the algebra E, just the equivariant X algebra from F to itself. Like before, we had the direct image from a Springer resolution. So our F was the direct image of the Springer from Springer resolution, and our T was nothing before, but now T will be some torus, and again, it contains the equivariant cohomology of the point, and we know this is the algebra of functions on the Lie algebra of our torus. So it contains this algebra in the center. So in particular, we can specialize this script E algebra over any point of our Lie algebra T. Sorry. 1 moment. And we obtain a specialized algebra. And this will be just a finite dimensional algebra already. So this is very similar to taking the specialization of the affine Hecke algebra, HA, what we denoted before. Okay, so we had this big center of the affine Hecke algebra, and we could specialize at any point of this center. And what we obtained was some finite dimensional associative algebra. And the same thing happens here. We get an algebra with a big center. The big center is just the equivariant cohomology of the point. But now, for the affine Hecke algebra, it used to be the Lie algebra modulo the Weil group, and now there is no Weil group, just the Lie algebra of the torus itself, and we specialize at any point. And as before, all these specializations they may have some geometric meaning. So it usually happens. I mean, in various geometric contexts, that the specialized algebra E sub x has some geometric meaning. For example, if we have a resolution from M to N, and and X in hourly algebra gives rise to a one parametric subgroup in the corresponding torus. It's just a complex number. So this is one parametric subgroup in the torus, but it's not necessarily a closed subgroup. Yeah, then you can take its closure. And get T sub x in T. Okay, but then this closure is not necessarily one parametric. A subtorus, not necessarily one dimensional. I mean, it depends on so to say rationality. Yeah, because since this German T is the Lie algebra of torus big T, it has some. It's not just a vector space over complex numbers. It has some rational or even integral structure. And if this X is a rational point, then we will have the corresponding subtorus Tx will be one dimensional. If this X is very irrational, then this T sub x will be the whole torus T. Okay, and we can take the fixed points of this subtorus. And if the fiber product of the fixed point has a cellular decomposition, like we had in our example before for the nilpotent cone and its Springer resolution, then this algebra E sub x is just the Borel-Moore homology algebra of maybe let's call it Z, the variety of triples, and it's just the X algebra, but not a covariant anymore. Just X algebra of the direct image of the constant IC sheaf of the fixed point set to itself. Okay, so there is such a straightforward generalization of what we had before. So this is what I mean by the specialized algebra having some geometric meaning. Okay, and now we have to stop, and next time we will develop some more of this general theory of specialized X algebras and apply it to the usual Cardinalistic conjectures. Okay, so that's it for today. Thank you, and I am saving the notes. And please send me your data, passport data. I mean, if you don't have a pass to the new building, then I will try to get it for you for the next Monday. But you have to send it to me today. Okay, and I know that Vanya Karp already did, and Altaner Nigol already did, but he didn't come today. Okay, so I'm saving this. And now I will try to save the recording, or at least stop the recording. So if you don't have any questions, I will get busy with it, with stopping the recording. Okay, so then see you.
Thank you.
Welcome.
See you.
Thank you.